In 2023, a Lufthansa Airbus A319 lost both of its engine generators as it was heading to Amsterdam. Descending through 31,000 feet above the Netherlands, ELEC Gen 2 fault suddenly appeared on the ECAM display, meaning that the right engine generator had failed. 5 seconds later, presumably after the left generator also failed, suddenly the aircraft switched to an emergency electrical configuration, with its ram air turbine deployed to supply backup electrical power. At this point, the autopilot and auto thrust disconnected, and the only displays available to the pilots were the captain's as well as the ECAM. Eventually, the aircraft managed to land safely, and thankfully nobody was injured. But the only reason this was possible is thanks to the incredible redundancy that's built into the electrical system. So let's go and figure out how this works. As an example, in this video we're going to take a look at the electrical network of the Challenger 650. To start the engines, we need electrical and pneumatic power, but in flight, these sources of power are usually provided by the engines themselves. So how do we bootstrap the aircraft when it's completely cold and dark? The first thing we need to check is if the battery itself is physically connected. Now you might ask, why do we need this physical connection, especially since there's already a battery switch on the overhead panel in the cockpit? Surely both the switch and the connection achieve the same thing. However, once we connect it, even when the battery switch in the cockpit is off and all the displays are dark, a small number of electrical components already receive 28 volts direct current or DC power through the main battery direct bus. You can see an electrical bus as a central hub that safely distributes power to multiple outgoing circuits or devices. The ADG at the bottom here stands for air-driven generator, and it's essentially equivalent to the ram air turbine that we spoke about with the Airbus story in the beginning. Its only purpose in life is to serve as the last resort in the event of a complete electrical failure. Long story short, there's a circuit that checks if there's been a loss of electrical power, which will then automatically deploy the ADG to save the day in the case of an emergency. There's also a second battery in the back of the aircraft, which, like the first one, also needs to be physically connected. This is called the APU battery, and it exists primarily to start the auxiliary power unit. When we turn on the battery master switch, already we can hear noises and see systems coming to life. This is because the battery bus has now been connected to both the APU battery and the main battery through switches and diodes. This bus powers a huge number of components, but for our purposes there are only a couple to keep in mind. First of all, the left multifunction display or MFD is now available. And as we power up other systems, this will give us essential information about their status, such as the auxiliary power unit and the engines. We can also now get feedback on the status of the electrical system, which shows us a low-resolution representation of the true electrical network. But maybe most importantly, the display will allow us to see if there's a fire in either one of the engines or the APU, since the fire detection systems are also now being powered by the battery bus. However, the fire extinguishers themselves are connected separately to the emergency bus, which is powered by the APU battery and battery bus. Everything we've spoken about so far is part of the direct current essential system. This powers the minimum essential avionics and electronics to fly the aircraft safely, including a bunch of detection systems that monitor things such as oxygen, hydraulics, engines, and fire. In addition, the DC Essential system also powers important electronic controllers that regulate and control systems such as cabin pressure and the landing gear. All of these components are connected to one of 5 buses, the only one that we haven't spoken about yet being the DC Essential bus, which powers systems such as stall protection, the left PFD, thrust reversers, and flap controllers. The DC Essential System buses can be powered in various ways for redundancy. For example, since the battery bus is so important, it can be powered by 4 different sources. During flight, the bus is usually powered by 2 transformer rectifier units, Essential TRU-1 and 2, which convert AC power from the engines or APU to DC power. In addition to the DC essential system, there is also the DC normal system, which is similarly powered by two transformer rectifiers, TRU1 and 2. The DC normal system consists of two buses which mostly power avionics and any systems that aren't already being handled by the DC essential system, such as the right-hand PFD and MFD. Similarly to the Airbus, in the event of an AC power failure, it's only the captain's displays that will still function since they are part of the DC essential system. But how exactly they will be powered in that case is something we'll talk about later. The DC normal system also consists of two utility buses which power cabin amenities such as USB chargers, the galley, and the toilet. Finally, we also have the alternating current or AC system, which does all of the heavy lifting during flight. It provides power to the DC systems as well as the AC systems such as the landing lights, pitot and window heat, and flap motors and hydraulic pumps. The majority of these systems are distributed across AC buses 1 and 2, which also directly supply TRU1 and TRU2, hereby powering the DC normal system. Amenities such as the coffee maker and microwave oven are powered by the AC utility buses, which are also fed off of AC buses 1 and 2. The AC essential bus can be powered by either one of the AC buses or the air-driven generator, automatically switching based on which one is available. Furthermore, the AC essential bus also powers the battery bus and DC essential bus through essential TRU1, hereby automatically relieving both batteries in the event of an AC failure. As for the batteries themselves, they are also each charged by one of the two AC buses. Continuing the startup process, to get power from the AC system, we'll first start the APU using the APU battery, since now the APU control and APU start controllers are also powered by the battery bus. As the APU starts, we can see here that the starter draws a significant amount of electrical power to turn the main shaft, although once it's rotating quickly enough, fuel is automatically introduced to sustain the cycle. After this, the starter is disengaged and the APU only requires fuel to keep itself running. At this stage, we can engage the generator, which will convert some of the mechanical power of the shaft into three-phase 115-volt, 400Hz alternating current. Since we now have AC, we are able to provide power to all of the electrical buses in the aircraft, including the DC ones through the TRUs. This also means that the batteries are now no longer required to power the battery bus and DC essential bus. In fact, the batteries themselves are now being charged by the APU through the AC buses. The next step is to start the engines. Similarly to the APU, we first need to spin each engine's high-pressure shaft at a sufficient speed before we manually introduce fuel, which requires a lot of power. This power comes in the form of bleed air from the APU, which is fed through air turbine starters that extract energy from the flow and convert it into a torque that is used to accelerate the engine's high-pressure rotor. Then, finally, once the engines are started, we can turn on their generators, which will automatically relieve the APU's generator. As is also the case with the Airbus A319, each engine has an integrated drive generator, which consists of two parts. The first is a constant speed drive, which is basically a gearbox that converts the variable RPM of the engine into an approximately constant speed. If it wasn't for the constant speed drives, the frequency and therefore power of the AC current would fluctuate massively depending on the thrust setting of the engines, which would cause damage to electrical components. You can actually see here that changes in engine RPM do cause slight variations in the delivered AC power. The second part of the IDG is a generator which uses the constant speed shaft to output alternating current. The electrical network will automatically configure itself in the event that only one generator is available, since each engine by itself can provide enough power to both AC buses. but even if both engines and the APU would fail, the air-driven generator would still save the day by single-handedly powering the AC Essential bus. As for the reason why the generators failed in the first place, Airbus managed to determine afterwards that the hydraulic blocks inside the constant speed drives were worn, hereby leading to an incorrect regulation of the drive's output speeds. To protect the electrical system from the resulting fluctuating AC frequency, the generators automatically disconnected, causing a loss of power and the deployment of the ram air turbine. Afterwards, the pilot started the APU and managed to reset the generators before making a normal landing at Schiphol. Thank you so much for watching, and I hope to see you again soon.